Hi, welcome everyone. I am Dr. Rajkumar from School of Physics and Material Science, Thapar Institute of Engineering and Technology, Patiala. So in this video, we'll discuss about Euler method of solving differential equations. The topics which are to be covered in this video are Euler method and its modified version, the modified Euler's method. So the Euler method, also called forward Euler method, is a first order numerical procedure for solving ordinary differential equation with a given initial value. For many of the differential equations we need to solve, there is no reasonable algebraic solution, however, that is, we can't solve it using the techniques of direct solving the differential equations. In such cases, a numerical approach gives us good approximation. So Euler method is a technique used to analyze a differential equation which uses the idea of linear approximation, where small tangent lines are used over a short distance to approximate the solution to an initial value problem. So let us move on to the graphical description of this method, that how this method gives you solution. So consider the equation dy by dx is equal to function of x and y, and given initial values are at x is equal to 0, y is y0. So we have given the initial points. So let us consider a function of x and y represented by this green line, and we have given x naught and y naught. Say point P is given to us, initial value x naught and y naught. Okay, and we want to calculate the value of y at next point, say x1, which is x naught plus h. So x naught plus h. We want to find the value of y at this point x1 on green line. Okay, because this is the actual solution curve. So we want to find this. So what we'll do in this method is, let us approximate the curve by tangent at point P. So if we draw a tangent at this point P, represented by this red line, so it touches at this point P. So it's a tangent on the point P, x0 and y0. Now the ordinate at x1, ordinates mean y value, x1 which is x0 plus h, meets the tangent line at point P1. So if we draw a vertical line, so from x1 it touches the tangent at point P1, represented by this dot, black dot. So this point is now x-axis, x coordinate is x1 and corresponding y coordinate is y1, and you see that there is difference between this value on green line and this value on red line. So this is the error. Okay, so now y1 is given by y0 plus r1 and p1. So if we draw it perpendicular from point P onto this line from x1 vertical line, and if we assume that this angle is theta, so then value y1 is given by y0, which is same y0 plus p1 r1. So y0 plus r1 p1, p1 r1, which is equal to y0 plus, in this triangle we have r1 p1 is equal to p r1 tangent theta. Okay, so now what is tangent theta? Slope is given by tangent theta, so we substitute tangent theta is slope, so also slope is given by dy by dx at which point? Point number P, point P. So y1 comes out to be y naught plus h times dy by dx on point P, this one, and on simplification y0 plus h, and we substitute the value of dy by dx, which is f of xy. At point P, x and y have value x0 and y0, so f of x0 and y0. So simply value of y at next point, that is y1, is equal to the previous ordinate y0 plus step size h multiplied by function at initial point x0 comma y0. So this is the Euler's formula. So in general, for finding the value of y at any x can be written as yn is equal to yn minus 1, previous one, plus step size and function at previous point, where xn minus 1 is equal to x0 plus n minus 1 h. Okay. Now this approximation or equation is called Euler equation, and this method is Euler method of finding an approximation solution to dy by dx is equal to f of x comma y, this kind of equation. Now what we observe from this method is, since we approximate the solution curve with tangent line in each interval, so unless h is small, the error is bound to be quite significant. So in order to get better accuracy, we have to take smaller step size, and this method is very simple but very slow as well. So these are two observations from the graphical representation of this method. Now let us consider a numerical for understanding this method, how it works. So using Euler method, find an approximate value of y corresponding to x is equal to 1. Okay, given dy by dx is equal to x plus y, so function is x plus y, and y is equal to 1 when x is equal to 0. So these are initial values which are given, and f of x comma y is x plus y. So given is value of y at x equal to 0 is 1, and we have to find value of y at x is equal to 1. So x is equal to 0 value is given to us, we have to find value of y at x is equal to 1. Let us divide the interval into 10 points, say n is equal to 10. So step size becomes, we have given value of x is equal to 0, and we have to find value at x is equal to 1. So we divide this interval 0 to 1 value of x in between 10 small subintervals, so that step size becomes small. Step size we have kept it small, we can increase it as well, but if you keep on decreasing the step size, your accuracy will be more. So the various calculations are shown in this table. So we have x starting from 0, whose value of y is given, simple, and then in step of 0.1 we are moving towards 1. So corresponding value of y we have to calculate. First value is given, and third column represent dy by dx is equal to x plus y. X plus y is function f of x comma y. So value of function is given. Function is y. Value of x and y are given initially. So x value is 0, y becomes 1. So function become x plus y, so which is 1. Now apply Euler formula. So new value of y, which is y1, is equal to old value of y, y0, plus step size into dy by dx, or f of x comma y, any of these notations, either left hand side or right hand side. So new value of y comes out to be, on substituting these values, 1.1. So we know that now we started from x is equal to 0, we get value of y1 from Euler formula. So we have y1 at what point? 0.1, because we have taken step size 0.1. So we have value of x 0.1, and its corresponding y is, we have already calculated, 1.1. So now we have to repeat the same step again. Now 0.1 plus 1.1 gives us 1.2. Again new value of y, after substituting these values we get 1.22. So for 0.2 now we have 1.22, and keep on repeating the iterations until we get at 0.9. So at 0.9 the new value of y comes out to be 3.18. So we have to stop here at this point, because by using the value 0.9 we have reached the value of y at 1, because if we start from 0 we have value at 0.1, we start from 0.1 we have value of y at 0.2, similarly we have 0.9 x, then we have value of y at 1. If you calculate value at initially from x equal to 1, then this value of y which will be calculated by you comes for x is equal to 1.1. So you have to stop a step before, because this is the newer value as compared to 0.9, and newer value is in the step size 0.1, so this value is 3.18 for x is equal to 1. So this is how Euler method give you the solution. Okay, so this one is the final answer. For x is equal to 1, y value comes out to be 3.18. Now this method is slow, we have another method, that is modified Euler method. So in Euler method, the curve of solution in each interval is approximated by tangents. So this is the previous figure in which we are explaining that tangents are used for approximating the curve, keeping step size small. Now tangent at P is drawn such that P1, value of P1 from Euler method is y1 is equal to y0 plus h f of x0 comma y0. This is from Euler method. Then slope of the curve of solution at P1 is, now slope at P1, so dy by dx at P1 is f at what point? x0 plus h, which is x1, so x0 plus h comma y1. This is computed. Now we find a better approximation to y1. In superscript in bracket we have 1, which means for first iteration. So y1 for of y of x0 plus h by taking the slope of the curve as mean of the slope of tangent at P and P1. So in Euler method we have slope or tangent at point P only. Now in modified Euler method we have tangent at 2 points P and P1, and we are taking the average of the slope of the slope at these 2 points. So y1 in first iteration comes out to be previous or old value of y0 plus h by 2. H is the step size and 1 by 2 is because we are taking average of these two values. So f of x0 y0, which is slope at point P, and f of x0 plus h comma y1, slope at point P1, because dy by dx is equal to function. So we are taking average of the tangent in order to reduce the error. As slope of tangent at P1 is not known, so because x0 y0 are given and we don't know about y1 slope, so we take y1 as found from Euler's method. So we have initially took help from Euler method and insert it on the right hand side of our equation. So this y1 is coming from Euler method to obtain first modified value of y1. Okay, so this y1, for obtaining the slope, we have to use Euler method, substitute the value from Euler method, and keep on refining using this formula. This is the modified Euler formula. Again, second iteration can be done for finding a still better value of y1. So for a second iteration, 2 is kept in superscript corresponding to the same point x1. So now for same point x1, you are doing iterations to get better accuracy in the value of y1. So y1 for second iteration comes out to be y0 plus h by 2, f of x0 y0 as it is, plus f of x0 plus h, that is x1 comma y1. Now y1 of first iteration. Okay, so first we have imported the value of y1 from Euler method, and for second iteration we are using value of y1 obtained in first iteration. So these steps can be repeated till two consecutive value of y agree. Okay, so this will be taken as starting point of next interval, and so on. This method is the modified Euler's method with better accuracy. So let us consider the same numerical using Euler method. Find approximate value of y corresponding to x is equal to 0.2 now. So the function is same, dy by dx is equal to x plus y, so function is x plus y, and initial values are also same, y is equal to 1 when x is equal to 0. So given values is same, y at 0 is 1, and we have to find the value of y at x equal to 0.2. So in previous numerical we have calculated value of y at 1 in the steps of 0.1. So we have calculated value of y at point 1, x is equal to 0.1, 0.2, 0.3, so on up to 1. So let us again take the step size 0.1. So the value calculated are shown in this table again. So value of x, initial value is 0, function is x plus y, which is dy by dx. So it is given at x is equal to 0, y is 1. So x plus y comes out to be 1. Now mean slope, since this is the first step, so we are using Euler method. There is no slope, so we are calculating new value of y from Euler method. 1 plus 0.1 into 1 mean slope, since there is no slope, so it will remain as dy by dx. So it comes out to be 1.1. Okay. So y1 from Euler method. So first line is Euler method, since there is no mean slope. Then at point 1, x is equal to 0.1, x value of function is 0.1 plus 1.1, which we have calculated here. So slope is 1.2. Now mean slope is 1 by 2. Initial value of tangent or function at point P, which is 1, and at point P1 we have 1.2 now. Okay, so now we have mean slope. So the modified Euler formula is 1 plus step size into mean slope, which is 1.1 now on solving this. So finally we have new value of y, 1.11. Again we have to repeat same iteration at point 1. So x is 0.1, new value of y is 1.11. So slope changes 1.21. Okay. In finding mean slope, remember that we are keeping the slope at point P same, because that is the value we have given, x0 and y0, exact value. So we are not changing the slope, but we are changing the second one corresponding to P1 point, 1.21, this one. So again, new value of y comes out to be 1.1105. Again we have to repeat the same step for the x is equal to 0.1. So again function value is 1.2105. Mean slope is again slope at point P and newer slope at point P1. So new value of y comes out to be 1.1105, which is same as that of previous one. So we have to stop here. Okay. So at x is equal to 0.1 we have new value of y, which is 1.1105. Okay, since last two values are equal, so we take y at 0.1 comes out to be 1.1105. So now this is the new value of x1 and y1. So x1 is now 0.1 and y1 is now 1.2105. Sorry, the value of function is x plus y, 1.2105. Okay, now we have better slope at P1, but we do not have slope at next point P2. Okay, P2 corresponding to x0 plus 2 times h, which is 0.2. So again we use Euler method and we calculate the new value of y, 1.2316. Okay, then for x is equal to 0.2, so we have value function is x plus y, so 0.2 plus value from Euler method 1.2316. Mean slope is slope at point P1, which is 1.2105 corresponding to P1, and slope at point P2, which is 1.4316 corresponding to this one, point P2. New value of y using modified Euler method now comes out to be 1.2426. Again, so value of y from Euler method changes from to 1.2426 using modified Euler method. Again we have to use this revised value of y in modified Euler method. So again repeat for 0.2. So x is 0.2, new value of y is 1.2426. So mean slope is slope at P1 and newer slope 1.426 after doing the summation, and new value of y using modified Euler method is 1.2432. Repeat the same step new value comes out to 1.2432, which is same as that of previous one. Since last two values are equal, so we take y at point 2 is equal to 1.2432. Okay, so this is how this method work, modified method. For these four lines, these are four lines corresponding to one line of Euler method. Okay, so for one row of Euler method, there are four rows in modified Euler method. For example, if we are repeating the values in fourth row, third and fourth row. So this is how we are refining the value of y, or we are decreasing the error in Euler method by doing more and more iterations in modified Euler method. So this is all about the modified Euler method. So in this video we have discussed about Euler method, need of Euler method, graphical representation of Euler method, then limitations of Euler method, and its modified version, modified Euler method. This modified Euler method is the faster one. So thank you for watching this video.